Every single time you stream a video, make a phone call, or even just scan a QR code, you're counting on a hidden mathematical language. It's this incredible science that ensures our digital messages get where they're going perfectly intact, fighting a constant war against the chaos of the physical world. So today, let's pull back the curtain on the invisible genius of coding theory.
All right, so here's our game plan. First, we're going to tackle the fundamental problem, noise. Then we'll meet the genius who proved a solution was even possible. From there, we'll dig into the magic trick behind it all, redundancy, and take a quick tour of the most important codes out there. We'll see them in action all around us, and finally, we'll appreciate why this whole field is the true, unseen backbone of our digital lives.
Okay, first things first. Before we can find a solution, we have to meet the bad guy in this story, the fundamental villain of all communication, and that villain is noise. I mean, really think about this for a second. These are things we just take for granted, but they're basically technological miracles. A deep scratch on a CD, that should turn the music into a garbled, unlistenable mess, right? And a crystal clear image sent all the way from Mars, through millions of miles of radiation-filled space, that should be completely fried. But it's not. So why? The answer is all about defeating noise.
So in this context, a channel is really just anything a message travels through. It could be radio waves zipping across the solar system, or it could even be time itself, like data just sitting on a CD for years. And noise? Well, that's literally anything that tries to corrupt that message along the way. We're talking static, physical damage, random cosmic rays. It's the universe's natural state of chaos trying to break our precious ones and zeros.
So, with this constant, relentless barrage of noise trying to wreck all our data, how do you possibly fight back? Well, this is where the hero of our story comes in. A man whose ideas lay the entire foundation for the digital age we live in today.
This is Claude Shannon, and back in 1948, he published this paper that changed absolutely everything. He didn't just offer a little fix, he proved, mathematically, that near-perfect, error-free communication over a noisy channel wasn't just a fantasy. He showed it was a theoretical certainty. He basically drew a finish line for all of modern engineering to aim for.
And his core insight was so profound. The way to beat noise isn't about brute force. It's not about just shouting louder, just cranking up the power on your transmitter. No, the solution is way more elegant. It's about being smarter. It's about adding extra information to your message, but in a very specific, carefully structured way.
Okay, so what does this smarter communication actually look like? The key, the magic ingredient, is a powerful concept called redundancy. But hold on, it is definitely not what you probably think it is.
This slide nails the difference perfectly. On the left, you have the simple way. Just repeat yourself. You want to send 101? Okay, just send it 3 times. 101, 101, 101. But what happens if the receiver gets 100-101-101? An error happened. But where? You can't be sure what the original message was. It's still ambiguous. But now look at the right. This is smart redundancy. We don't just repeat 101. We encode it into a longer, special code word that has a mathematical structure, and that structure is the secret sauce. It allows the receiver not just to detect an error, but to pinpoint its exact location and fix it.
Let's look at the simplest trick in the book to see how this works. It's called a parity check. So you have your data, 10110001. First, you count the ones. Here we have 4 of them, an even number. So we add a single parity bit to the end, a 0 to represent even. Now the message flies across the noisy channel. If it arrives on the other side and the number of ones is suddenly odd but that parity bit is still a 0, bingo. Alarm bells go off. The receiver knows instantly that an error has happened. It's a simple idea, but it's the very first step into this amazing world of error correction.
All right, so that simple parity check is really just the beginning. From that basic idea, we've developed these incredibly powerful codes that, and this is no exaggeration, run our modern world. And you need different kinds because, well, not all noise is the same. You need different tools for different jobs.
First up, let's meet Reed-Solomon codes. These guys work on chunks, or blocks of data, and their absolute superpower is correcting what we call burst errors. This is when a whole string of data gets wiped out at once. The perfect example? Think of a deep, nasty scratch on a DVD.
And this is exactly where you find them. Reed-Solomon codes are the reason that scratched-up CDs still play your favorite song. They're why a QR code with a big smudge on it still manages to scan. And they're a huge part of why we can get reliable data back from probes at the edge of the solar system. Anytime you have damage that happens in a big clump,
These are the codes that save the day. So if Reed-Solomon codes handle big, chunky errors, what about the other kind? That's where convolutional codes come in. Unlike their cousins, they don't work on fixed blocks. They're built to process data as a continuous, flowing stream, and this makes them absolutely perfect for fighting off that random, scattered, persistent interference that you get in wireless transmissions. And trust me, these things are the unsung workhorses of our connected lives. That mobile phone call that stays crystal clear even as the signal bars drop, that's convolutional codes at work. Your Wi-Fi signal staying strong even when the microwave is on? Yep, that's them too. They are the silent heroes keeping our wireless world from dissolving into static.
So, we've met the big players. Let's really tie it all together now and see the direct line between a specific real-world problem and the clever coding solution that makes our technology just work.
This table is really the key takeaway. It lays it all out. You've got a burst error on a CD from a scratch, you throw Reed-Solomon codes at it. You've got a continuous stream of interference on your mobile call or Wi-Fi. That's a job for convolutional codes. And for the ultimate challenge, a deep space probe getting hit with random cosmic rays and facing potential equipment failures, you don't pick one, you use a powerful combination of both. It's all about matching the right defense to the right kind of attack.
Okay, let's just zoom out for a final thought on why this quiet, deeply mathematical field is just so incredibly important.
It's really not an exaggeration to say that without coding theory, our digital world would simply collapse. It would be impossible. It is the foundational pillar that no one ever sees. It's the silent mathematical language that translates the chaos of the physical universe into the order and reliability our digital lives depend on. It's the trust layer for every piece of information we send and receive.
And that leaves us with a really fascinating question to think about, doesn't it? We've just uncovered one of the most important invisible languages that holds our modern reality together. So it makes you wonder, what other hidden systems, what other invisible languages, mathematical or otherwise, are being built right now that are going to quietly shape the world of tomorrow?